report on the goings-on in the physics world.
And I am your special correspondent.
Today we will be learning about potential and kinetic energy. This just in, Anna is getting her retainer case. And now to our correspondent in the field.
I have my retainer case.
Go. Our topic today is kinetic energy. Kinetic energy is the energy of motion.
Get set, go.
Right, Taylor. That's my favorite type of energy.
That's a powerful statement, Anna. Can you tell us any more about kinetic energy?
Well, that's a great question, Taylor. Kinetic energy is represented by the equation Ke is equal to 1/2 mv squared, or m is equal to the mass, and v is velocity.
Right, Anna, but you forgot to mention that kinetic energy is measured in joules, which is a Newton times a meter. Here are some examples of kinetic energy.
This example of kinetic energy is of a mad woman running across the lot. As you can tell, she's running in velocity that is constant, and there is her mass also running in a constant velocity.
Now for another example.
Now it's time to realize our potential. Energy?
Romeo, Romeo, wherefore art thou, Romeo?
Dude, I'm right here.
Hi, omnipresent narrator here. I just wanted to drop in and let you know that this scene from Tony Award-winning production of Romeo and Juliet has an excellent example of potential energy in it. Juliet, standing high on her balcony, has much more potential energy than Romeo, standing here on the ground and chewing on a stick.
Oh no, Juliet's falling! She's about to turn into kinetic energy!
Potential energy, you might ask. How is that related to height? Well, truth is, the more height you have, the more potential energy you have. Same with mass.
It's so pointy!
I'm back. Here we have the charming figure of Juliet with all of her mass, standing on top of the high H cliff with Romeo at the bottom. Clearly, you can see that if we're following that equation, Juliet has more potential energy than Romeo. She also has more regular potential than Romeo. Take a close look.
Thank you for that interesting special. So far, we've mentioned one type of potential energy, gravitational. Now, we'll take a brief look at two other types, spring and electrical.
Here we have spring potential energy, where distance is represented by x and the constant is represented by k. Also in this drawing, we have a spring with a bit of kinks in it, as you can see here.
That's kinky! Spring potential energy is represented by these equations. Spring potential energy equals 1/2 Fx, or spring potential energy equals 1/2 Kx squared. Electrical potential energy is when a charge is moved to a place where it does not want to be, usually towards a like charge. In this case, it is demonstrated by the fact that Maddie, the mad woman, does not want to be moved nearer to Anna. Electrical potential energy is represented by the equation KQQ over R, or Q times V. Here, K is the electrostatic constant.
Here is the simple example of conservation of energy. Please ignore them. Here, potential energy becomes kinetic energy. This means that mgh is equal to 1/2 mv squared. If you're calculating, the m's cancel.
Example.
Potential to kinetic. Here is a more complex equation for the conservation of energy. Pay attention. Here, potential energy before plus kinetic energy before plus the work by non-conservative forces is equal to the potential energy afterwards plus the kinetic energy afterwards. It's brilliant, people. Brilliant. Such examples of this are on race cars or wait, why did I say that?
Continue with us.
Some examples are on roller coasters, where the work by the non-conservative force is friction. Shh, don't tell anyone. Friction likes to keep it a secret. But that's how energy is lost.
Thank you for joining us today for our special broadcast on potential and kinetic energy. Thanks to special contributions from Mr. Pallid and Mr. Fullerton.
Goodbye and good night.